Do you guys have it? Okay. Here.
Oh, you already submit something. Thank you. And this goes on.
This is everyone's.
Thank you. So it goes on the record. Homeworks are submitted in time.
One of the few.
Huh? No. Everything is good. I'm just checking. I was giving this quiz also to some faculty of our university, and one of them failed.
But were they experimentalists?
No, to theoreticians.
Oh.
So you are
Oh.
doing better than some of the.
No.
Everyone is better than some faculty of the school. It's not friendly. I need to cut it from the recording. Yeah, one needs to think before saying something.
But
I can mute microphone if I know that I'm going to say something.
saying that on this specific thing, they might not ever use this specific theory, so why would they need to know?
No. It's not good to declare any non-positive information
Oh.
if you want to keep everyone friendly.
And then if you want to get tenured, you get mad at you.
It is important, but there are more important things because, like, global reputation. So, what are we going to do? There will be three. Hello, camera. There will be 3 slides scientifically, so we can do them in 3 minutes by the end of the meeting. And I will just introduce very briefly functional form of functionals. Right now we are aware only of local density approximation functional and spin resolved LSDA. We do not need more for general education and for being successful writers of papers. But just in case, I will distribute several handouts and show generally how it looks like. So if you see it in literature, you will get scared. And most of the part, like 40 minutes out of 50, we will talk about the last chapter of our class. So when we meet tomorrow in the lab, we will complete the last part of the practical skills. So, and when you present on Thursday, you all will become certified experts in electronic structure, ab initio molecular dynamics. You will be ready for independent research. And since semester is closing very soon, starting from Thursday night, I will be thinking only about research projects in the course. From time to time, I will come and present a little bit more equations just to entertain you, but it will be not the goal. Goal is to complete research. And since today is an election day, we should elect subjects for the research. Maybe I will distribute the. So there are n+1 pieces of paper, identical. One is for everyone to put first and second choice. Another 10 are just for your information, so that you can look what have I selected and keep it as a little memo. And also I have sent it as an email attachment. So please write your first and second choices, and do not rush. You have time until the end of the meeting. You can prepare. If you do not like any of this listed ideas. Feel free to write down what you're interested in. You are welcome. And we can discuss in one-to-one.
Yeah.
So, substantial part of today's meeting, I will spend time on overviewing these subjects and telling what they are. So, if you haven't developed your idea, do not rush. There is time. I will do some announcements and then I will go over all of them or most of them and tell something.
I saved some of these pages in my lab.
So this is the most important piece of paper for the rest of the class or for the whole class. I will be distributing like a lot of kindling papers that you do not care about. You can glance through and throw away. So keep this one with you, and the rest you can just put it on the edge of a table and swipe it over by the end of the meeting. So I do see very healthy progress in previous homeworks, which are, I think, great too to get some skills in what we will be doing for the research. And although, well, there will be very, very simple homework for the coming weekend, which will be completely related to the project. So done with general education. You are all already educated. Enough. In the time limits of the course, you are very educated. I have no doubts. But for the, like right now, probably you do not think of anything except presentations. And it is fine, so I will be just hypnotically communicating some information that you will remember on Friday morning. So upon you select your project, it will be reasonable if we do not wait until the next lab and prepare the atomistic models for the selected research project. And by the coming Tuesday or by the coming Wednesday, by the lab, you prepare the model and maybe make some very preliminary introductory steps of like plotting the structure itself and plotting the density of states. So something that will be 5 times easier than 2 previous homeworks. So because I admit it was a little too much. The previous 2 homeworks were really on the edge of human abilities, and I hope that we do not repeat this amount of efforts. So your effort in completing them and doing those is very appreciated. So here is homework related to the research, but it is a whole page of writing, but basically it means just select model and prepare coordinates. Okay. And there will be several handouts for the scientific part, but I will distribute them later when there will be time to talk about science. Now, let's go to some introduction of the research. Good. focus. Okay. So we are, well, I'm trying to keep continuous numbering of our meetings, but the one that includes general functional form of density functionals is overlapping with a lot of administrative discussions. So we are still on the meeting number 22 with letters A, B, C. But the number for our meeting on the practical skills is 23 for like Iron Strong. And then we'll continue the continuous list. So the research projects, they all are related to molecular dynamics. Even if you are interested in static properties of some compounds, there will be important component to see how the properties of a molecule are affected by the thermal vibrations. And I think it is a unique strength that you get in this class compared to basic accumulation of quantum chemistry skills. So it is a little accent in what we do compared to like maybe 100 other classes in computational chemistry. For example, if you do spectroscopy of metal ions, either in crystals or in organic ligand environment, upon heating, the coordination number may change. So that drastically change spectroscopy. Or upon heating, it may, well, it's all connected. The change of coordination number may lead, change the splitting and then induce a crossover from between low and high spin. So even if areas where one should look primarily on ground state calculations, there is a influence of heating that we shouldn't forget it. Another chapter is reaction dynamics, where we can either bring together reactant and product, heat them and see what happens, hoping that bringing together several reactants and looking if they will develop into a product. It's very general setup for calculations, and one can do it almost blindly. Just prepare models, heat, and see what happens. There is a modification of this philosophy. If the reaction and mechanism is partially known, one can formulate it into the scattering or collision problem. When one has a substrate, maybe a metal substrate, and reactant can be prepared as a single molecule, bombarding the catalyst, bombarding the substrate, bombarding the catalytic site of enzyme. So coming to the right spot with a developed velocity, or maybe a molecular beam of several reactant molecules approaching the catalytic surface. And then this kinetic energy of approaching may induce additional reactions compared to what they would do if they just adsorb. So just bring together and heat, one option, or specifically prepare the momentum for reactant approaching, reactant 1 approaching reactant 2. Well, if we are looking into reactions, there are several options for etching of nanomaterials with reactive substances, like hydrogen peroxide may drill holes in something. The combustion, bringing together the fuel and oxidizer and see how they form products, and maybe there are several products. There is broad range of possible projects related to photovoltaics and charge transfer. So how the photo-induced excitation of a model is resulting into formation of charge transfer, which can be explored just statically as a just availability of such states, or on the dynamical aspects. What are the rates, the speed of formation of this charge transfer? And also for each of the excitations, one available skills that we have accumulated by now are sufficient to compute the lifetimes, such as radiative lifetimes, which is an observable that can be compared to experiment. Some of the possible projects are related to conductivity and sensors. When one modifies conductor or semiconductor by adsorbing molecules or just slightly functionalizing, it drastically changes conductance, and it can be used like in smoke detectors or something electronic nose that will recognize several smells. As you have seen from last homework, the last which you were doing this weekend, which was supposed to turn in today, although there is an extension for like presentations are priority. Homework is good, but it is secondary, and if you bring it a little later, it is fine. So, but in this last homework, you were seeing that even if you do not launch dynamics, if you just change electronic configuration, the nuclear arrangement, the interatomic distances may change. Sometimes it is not visible by human eye, but some bonds are contracted or elongated. For example, you may have seen, and may have some of you have written comments to the homework, that upon creation the anionic species of this transpolar acetylene, the bonds becoming longer and system becomes less stable. So it is about to decompose. So this change of bond lengths, change of nuclear configuration upon changing of electronic configuration, especially upon charging, is referred by word polaron. And one can do a project related to polaron formation in any material, like conjugated polymers or nanostructures. So another chance. So high to low spin crossover. If you are interested in metal organic complexes, it could be your choice. Interfaces. When we get the skills in this specific class software for solids, it can deal with interfaces of solid substrates and liquids, or solid substrates and gases, which is important for surface chemistry. So one can formulate a decent surface chemistry research project. And the challenging and ambitious project that, or component of any project, is the non-radiative rates of non-radiative transitions between electronic states. This is a little harder than one can do in the remaining month, but one can formulate it and do it with a little help. So some of the projects have marks assisted, which means in recognition of very high level of difficulty, those who select those projects will get additional help. And by low size font, there are additional projects that I don't know how to organize, but you can, maybe you may find something near and dear to your heart or to your research interests. So there is a complete freedom. You vote, you elect what you like to do, but upon you select what you want to do, it will be the plan for the remaining month to investigate. So one of the possibilities is to explore dopants in crystals, like not metal organic complexes, but metal ions in crystals, which are background for lasers. I'm not sure that anyone will select it, but there is a possibility. And it is also an assisted project. Also, somewhere there was listed interface between metal and semiconductor, which is a very standard problem for a broad range of material research, like photocatalysis, photovoltaics, and general catalysis, when one deposits catalytic objects on a solid substrate. So, general plan of your last homework and of your future research. If you do not know what to do, you just prepare your model in optimized and thermalized configurations and compare the basic observables that you know how to do. And sometimes it is sufficient to answer the to satisfy your curiosity and learn something new about the model. If you know more what you want to learn about the model, we can modify and make this plan more complicated in one-to-one discussions. But generally, if your goal is not excellence in research project, but just completion of the course, this will be sufficient. So, how do we do it? Take a model, change configurations, and then do this thermalization, molecular dynamics, and then density of states absorption spectrum for different configurations. Same as in the homework that was due today. Well, this is too generic. This is it is not possible to create general research plan for any material and for any challenge. Otherwise, we will have no right to exist as scientists. If it will be so easy, then robots will do research. So there should be modifications to these plans. Some steps can be eliminated, some can be added. So it is just an average starting point. So if you tell to yourself, "Oh, I never did research project. What should I do?" Bless you. So just modify electronic configuration. For each electronic configuration, do molecular dynamics and explore spectra, density of states, do spin polarized calculations, and then you will learn something new. Okay, so a little entertainment. Here are some projects that were done in the similar course in previous years, and I'm not showing all of them were resulted in the scientific papers, so the seeds of research projects in class were serving as the starting point for big research paper. So here is similar to what one of the attendees of this class presented yesterday. So it's photo-induced reaction dynamics for decomposition. Here it's not self-exploding molecule. It is induced decomposition and fragmentation of metal organic complexes in order to chemical vapor deposition applications. So one can see that in the excited state molecular dynamics, one has a sequence of bond breaking, bond formation events, and there is a development of several products, some of which look exotic. So there is a hydrogen elimination, acetylene elimination, and a number of products is bigger than number of reactants. I'm just entertaining you. It is neither me, no students from previous year class. It is just an image from video from YouTube, but it was a spark for doing one of the projects for unstable molecule approaching catalyst and going through decomposition reaction. So this is one of the projects completed in previous years when hydrogen peroxides approaching silver cluster and decompose on the O2 and H2O. So it is, even without electronic configuration, just molecular dynamics of a reaction. I don't know how to make the sound less loud.
Yeah. Do you turn it off in the monitor?
No, then it will disable our conversations.
Oh.
So prepare your earplugs if you do not like sounds. So it is another project also done as a part of a similar course. So here is the setup was the metal catalyst prepared in active configuration with additional negative charge communicated to this lead, to this electrode, and then protons are approaching this metal catalyst, and upon they come into the contact with the surface, they are getting charge transfer, they are reduced, and they combine into molecular hydrogen. So it is prototypical modeling of hydrogen production. And it is not very challenging computationally, so if some same sort of calculations is very reasonable and practical to do in the remaining couple of weeks of the course. So we started with protons and ended with molecular hydrogen, which so proton reduction through decomposition. And here is an example of scattering of reactant from the substrate or from surface, where the molecular beam here is represented by 1 molecule of steam, 1 molecule of water with high kinetic energy, and it does approaches the silicon surface, and then there will be a chemical reaction. Sufficient to induce bond breaking in the surface layer and to break oxygen hydrogen bond and so form H2 molecule. And then this hydroxyl feels active enough to substitute the undercoordinated surface side. So there is a, well, it is a silliest possible way of hydrogen production. And it is illustration of water contaminating silicon, which upon hydroxyl it gets some states in the gap and is not good for electronics. One of the projects, if your models of your interest are very big, if you're dealing with biology-related molecules, it could be disabled for electronic structure, but you still can investigate some properties in the force field molecular dynamics range. So here there was a, I don't know how you can just there is a very big molecule container filled with gas. And if the temperature is low enough, it can hold very high pressure. Just molecular container holds gas. But if temperature is raised a little, then gas starts diffusing through pores and go away. So it is temperature activated container. So close your ears. Okay, it was going away. And another, good. And another application, if you are characterizing, if you are in experimental track and you're characterizing your materials, your molecules by spectroscopical tools, Typically, we do CW spectroscopy because it is so less expensive. But sometimes the dynamics of reactions need to be followed in the time-resolved regime. And there is a way to address this time evolution of spectral signal in time. Here is something related to time-resolved photoluminescence or stimulated emission of the excited state. So upon excitation of material at the bluish wavelength, as time passes by, it relaxes to lower transition energy. But as it goes dynamically, it is able to emit at different wavelengths what one can follow. So it's going from blue to red. Then it going stuck on the lowest available excitation, stays there long enough until it emits everything. So, and then one also can estimate the lifetime of the luminescence. Projects like this are possible, but this one probably is mostly numerically demanding, while others, molecular dynamics, are very doable very quick. Okay. I hope you got some entertainment and relaxation. Now let's go to the mode of collecting the handouts. You may collect them for the future, or you can throw them away right after the meeting. No? No? Yes. So it will be 5 sets of handouts, and they will, as soon as we look on these handouts and I show you 3 slides more, we will be done with density functional theory. So we do not pose a goal to develop density functionals. We know in general Thomas Fermi, local density approximation, and we know that there are higher order functions. But sometimes one needs to use different functionals, and one needs to repeat calculations with different functionals, because some of the functionals are better suited for molecules, some better suited for dielectrics, some better suited for metals, some are better suited for semiconductors, and some functionals are specifically designed to address charge transfer states. Okay, so there is the overlap is not as big for. It is possible to resolve any conflicts, although some subjects have more than one volunteers. It's possible, so there are no big conflicts. Everyone will be happy. So the handout that I have distributed is the list of notations. So I hope that no one of us needs it, but just in case, I want to prepare you for big life, where maybe you need to read papers that are not in applications but in theory development. And then there is a shock, because we are seeing that density functional theory is as simple as 1 to 3 flowchart. And when you look into true paper, they have like many lines of derivations which look either boring or scary. So, and sometimes they do not best possible job in explaining notations, because there are standard notations for developers of functionals. So one of them we introduced a couple of meetings ago. So the spin polarization, difference of alpha spin up and spin down divided by spin up plus spin down, with this zeta. And you also see that there is a Fermi energy as function of density. And this one R sub S, it is radius of such sphere that will contain approximately one electron. So if you have homogeneously distributed density of so many electrons, we can change the radius of sphere until it will contain amount of electron density equivalent to one electron. And it is a good parameter for theories. And most important thing that, well, nothing is important today, but if you want to rank it, the X parameter. So the idea behind this X is that when we all were in the first year of undergraduates and we just started calculus, we learned that any function can be, or most of the functions can be expanded in series, where the leading term is just value of function in the vicinity of a point, and second term is the derivative times increment. So anything can be approximately represented with help of the derivative, or if it is multidimensional calculus, then gradient. Same with functionals. When we were starting the very introductory level, we represented just functional as evaluated at single point, local density approximation. If you want to be a little more precise, then one needs to include gradient of the density. And since one wants to have dimensionless corrections, one tweaks the dimension in such way that it will be like, if we take derivative, the power is reduced by 1. And here it is power 4/3. So this X will have dimension rho in the power 1/3, which is the same power as the exchange correlation potential in LDA, rho to the power 1/3. If you're talking not about total energy, but the potential. So it is convenient parameter, but most of the idea, one needs to have the functionals including the gradient of the density. Idea. Practical implementation, one uses gradient divided by density in the power 4/3 as a parameter for some advanced equations. And if one applies some very scary, terrible long equations, depending on this one calls it GGA, Generalized Gradient Approximation, because there is gradient. So if someone asks, like, you are showing so many results, which functional were you using? Very possible. You write your report, you invite your family member to come to this room and listen to your presentations, and your cousin asks you, which functional did you use? And with very high level of confidence, if you do not recall which, most of today's functionals are GGA, Generalized Gradient Approximation, with some gradient corrections. Good? Now I'm going to, this is more or less useful. Now I'm going to give you like 3 or 4 sets of handouts that are completely useless, or almost as good as useless. So they are a couple of pages from popular computational chemistry textbooks. They are trying to communicate the same information just from different angles, different point of view. Looking on these handouts, we will not make you a developer of functional, but just bring you a little bit of confidence in the terms, in the vocabulary they use. So I think this one is either, this one is Eero Levine. It is even not the electronic structure person. It is general physical chemistry textbook. And I will be giving you several handouts, but they all will show example of this B88 functional, which has the simplest way of correcting local density approximation. So it will contain a function of x, which we defined as this gradient to the specific power of density, and this inverse hyperbolic sign can be expanded as x minus some power expansion. So just do not be scared if you see equations like this. We do not need to program them. We do not need to write them. Most of the case, we just need to admit that they exist, and they look a little more complicated than LDA. Here is the main message of today's meeting. But just in case, I will distribute this pile of papers. So if you will look on the third page, here, I'm not sure if it is a good idea. Yeah, here. Then there will be the same equation as on the slide. So B88 exchange function. So we are getting used to see it. And now there is a...
Except for this one uses LSDA.
LSDA, it is what we did 2 meetings ago. So it uses it as a starting point and then adds corrections to it. So LDA and LSDA are equivalent if you deal with singlets, and LSDA is the only correct thing if you do spin polarized. So generally, one can tell that the functional depends on density in the first power and gradient of density. Typically, if you are writing a report of what you are doing, it is sufficient. So this equation 2,127 is probably very sufficient minimal verbalization of the typical functions. This book is written by Marx, not Karl Marx. Dominic Marx, who lives in Germany, but he wrote a book on the ab initio molecular dynamics. Okay, next two are from the Kramer and Jensen, which are standard text recommended for any university for computational chemistry. And you see it is the same pattern of introducing material. So presenting local density approximation and then telling very brief information about correction to local density with this gradient corrections. So if you look on the second page, equation 634, you will recognize the 1 minus zeta and 1 plus zeta, which shows the way how to go back from spin polarization to density up and density down. So if one meticulously goes through this equation, there is not much challenge. But since reasonable functionals are already developed, we are just using them. And understanding that there are about 100 functionals and each of them are addressed, abbreviated with the names of their developers. Like if you want to become famous, you design another functional and call it after your last name. So here you see another, it is by Kramer, no, previously by Kramer, this is by Jensen. So it shows very general way how to say what we are doing. So it shows that the energy is a functional as represented by rectangular brackets of the gradient divided by rho to the power 4/3. And I do have the last set of handouts, which you may appreciate if you liked the first half of the course with Gaussian software. So this is summary of density functional theory from Gaussian user manual. So how do developers of the code explain what they're doing? So it is their language. But generally, it is the there is no contradictions between different sources. They just explain it on, from different sides. So if you look on the equation 59, it will show the same B88 functional, because it is probably the simplest one to explicitly write down. All others will be a little more correct, but they will immediately take several pages of equations. Okay. So by now you have sufficient introductory level of knowledge of density functional theory. So we are not going to speak about density functional theory anymore as a theory. We will be using it only as a practical tool for our research. The practical applications will from now on become primary goal of the course, and the remaining bits of theory will be dealing with description of excited states, which need the density functional theory by itself, as formulated, is designed for ground state. When one tries to use DFT for excited states, is lowest order approximation. There are some theories designed for excited states, and we will be lightly going through them. I think we should finish now or very soon. Let me probably scratch just one equation to get us going for next meeting. So when we were meeting last time, we discussed right here in class practical skills of modeling excited states. And we were discussing of all orbitals that are occupied by electrons contribute to the total density. So we were making summation of all orbitals and placing weights in front of them. Good. It is correct, and it is what we do with Fermi weight. But there is a little upgrade of this equation that establishes a bridge for excited state theories. Ground state was summation of all orbitals up to infinity, occupation number times point-charged orbital per absolute value squared. Right? And those are partially charged densities. So it is what you were plotting in the homework. And this is what is determined by the Fermi weight keyword. By the way, I didn't make an accent in the class that this code word should come together with the I smear equals -2. So in the homework verbalizations, there is a link to a template of the correct in-car for excited state. But if you're trying to build in-car yourself, then this Fermi should go together with this one. By default, it is 0, and it means that use Fermi distribution from equation. If you want to manually set it up, then it should be -2. Okay. So this is summation I theta star times theta without star. So the indices here are the same, but without any scientific thought. If we just want to be mathematically rigorous and we see product of two functions, how do we know that the indices should be the same? Just silly mathematical experiment. What if the indices are different here? Summation ij theta star I theta j without star. So it is just a little expansion, a little more rigorous rewriting of this expression. So it means that in addition to the pairs of orbitals, conjugated and non-conjugated, where their indices coincide, one has also pairs where the indices are different. Okay. So this is density. And this is, originally it was occupations, but now it is a mathematical object with two indices that determine density. So since there are two indices, it is matrix. And since it determines density, it will be density matrix. So in a little bit more general approach, generalized approach, total density is composed of Kohn-Sham orbitals as product of any pair of orbitals multiplied by density matrix. If we are in the ground state density matrix will be equal to 1, 1, 1, 1 as many times as we have number of electrons divided by 2, if it is a singlet. And then the rest on the diagonal is 0, and the subdiagonals are also completely zeros. So if we set up such density matrix, then our new definition of density will be equivalent to old definition of density. If our system is perturbed, our molecule is perturbed by light, if it undergoes explosion, combustion, some perturbations, it goes away from equilibrium. And the components of density matrix away from diagonal and away from this lowest layers can get non-zero values. So what we will be focusing on for next time when we deal with theory, we'll be dealing how to get change of ground state density matrix upon photoexcitation. H nu goes to rho excited. Make sense? Good. Okay, last question for the day. Just trying to identify what is the border. Oh, everything below this line will be invisible. Invisible.
Is that a self-portrait?
No. And it is not a portrait of anyone in class. No. So, if we know that this element is corresponds to HOMO, and this one to HOMO, then how do we index the nearby elements? So just indices of density matrix. So I'm going to focus on this segment near HOMO and LUMO and write explicitly what are the indices. There will be no big signs, but it will be a little foot to the door. So we are going to look on the four by four table. So the one here will be layer of HOMO and HOMO. When we look for the highest occupied orbital and we have it multiplied by itself. Here, that in ground state it will be HOMO. Here we will have pair of orbitals HOMO and HOMO. In ground state it will be 0. Then the next one will be rho HOMO plus 1, HOMO plus 1. So here will be rho HOMO minus 1, HOMO minus 1 plus 1. So the other elements of density matrix will have indices HOMO, HOMO, LUMO, and here will be rho LUMO, HOMO, HOMO. Just swap the indices of highest occupied and unoccupied. And if you go further away, this will be yes, plus 1. This one will be LUMO plus 1, LUMO. What will be here?
1.
HOMO minus 1, HOMO, HOMO minus 1. Here will be rho HOMO minus 1, LUMO, rho HOMO minus 1, LUMO plus 1, rho HOMO, LUMO plus 1, rho LUMO, HOMO minus 1, rho LUMO plus 1, HOMO minus 1, and we have the last one, rho LUMO plus 1, HOMO. So before we were dealing only with diagonal part of density matrix. Right? And as soon as we jumped into excited states, we will be dealing with off-diagonal elements of density matrix that will get away from 0 if there are transitions between states. There are transitions from HOMO to LUMO or backwards. Transitions. Because there are transitions, those segments are Transition. So when we meet next time for the theory, we'll look a little bit more on this object. Would you approve completion of the meeting now? Okay. So here it's the same as you see on the blackboard. And somewhere I wanted to announce that we are done with the meeting. So the primary, well, two goals, two big goals and one small goal. Biggest goal for near time is please send me your slides for Thursday by Wednesday midnight. And as you have time, well, focus on presentations. Let's do not distracted by anything else. We will meet on tomorrow evening for completing the list of skills for presentations, and then we will keep talking about other stuff. Done. Meeting is dismissed. We are going out of records. I will stay here to answer questions.
We meet here tomorrow, not tomorrow.